Hi everyone, Mrs. Basega here, and today we're working on gravity basics. What do you need to know versus what do you already know about gravity? So for today, your job is to watch this video and take notes. Then use those notes to help you answer the Google form. I'll use that as today's check-in, so make sure you complete that before the end of the day. So here's what we already know. You actually already know how to calculate what I'm going to call the local force due to gravity. This is the force due to gravity due to the uniform field of objects that are close to the surface of a planet. Now, imagine everyone near the surface of the Earth. We could use the same 9.8 gravitational field for anything near the surface of the Earth, and thus it's easily calculated. We could use that the force due to gravity, or the weight of attraction between an object and a nearby planet, is equal to the mass of that object times the planet's gravitational field. And on Earth, the gravitational field is 9.8 newtons of force for every kilogram of mass. It's directed straight down towards the center of the Earth because even if you have this bumpy surface, all of the objects near the surface of the planet are attracted to the center. And since the planet's radius is so big, that always means downward. So I could use the 9.8 newtons per kilogram for the gravitational field of this owl that's flying through the air, or the schoolhouse that's actually on the surface, or a basketball that's shot into the air, or a school bag that's laying on the ground. I could use the local gravitational force equation in order to calculate any of those objects' weights because I know we're on Earth and I know the gravitational field of the Earth. If we were to move all of these objects to another planet, I would only need to know the gravitational fields of that planet in order to calculate the weight using this equation. Now, let's talk about the basketball for a second. The basketball has a force due to gravity that attracts it towards the center of the Earth. I can use the Fg equals mg equation to find the weight of this basketball because it's close to a very large mass, the Earth. But I also know Newton's third law. Newton's third law says that forces come in pairs. So if the ball is gravitationally attracted to the Earth, that must mean the Earth is also gravitationally attracted to the ball. These must be equal and opposite forces. That is, the forces that are interacting, the interaction between the basketball and the Earth, is a force that has the same magnitude, so the same size force, the same number of newtons, but in opposite directions along this radial line that connects the two centers of mass. That is actually going to be our r, the radial distance between the two centers of mass. These forces are equal magnitude, so if the ball is being pulled 5 newtons down and to the left, that must mean the Earth is being pulled up by 5 newtons to the right because of this mutual gravitational attraction. But the ball accelerates more than the Earth, and that's pretty apparent. We don't see the Earth move when a ball falls, and that's because the ball has less mass and therefore accelerates more. Mass and acceleration are inversely related to each other. By the same logic, the Earth must accelerate less because it has more mass than the ball. So Newton's third law, when applied to the gravitational force, says that both the Earth and the ball experience the same magnitude of force, but that same force doesn't accelerate them at the same rate because they're different masses. Okay, but that must mean there's a force that pulls upward on the Earth. And here's where Newton got his stroke of genius. He was thinking to himself, hey, what if the force that causes an apple to fall straight down and accelerate in this uniform gravitational field, what if that was the same force that would cause an apple to fall from space? If the apple were moving fast enough, it would orbit the Earth like the moon does. And so if those two forces are the same, then they must be able to be expressed similarly. So the result of this breakthrough was called the law of universal gravitation or the universal law of gravitation, and we believe it to be true of the entire universe. This law states that any two objects with mass are gravitationally attracted to each other. However, this is a harder equation to use than just calculating the product of mass times field. You should use this if you can't use the other one first. The nice thing about it is it's always true. So if you're concerned about trying to figure out which equation to use, at least you know that this one always works, while the local law of gravity only works if you're close enough to the surface of the planet. So here's your new equation. Make sure to write this one down. This equation is called the law of universal gravity or the universal law of gravity. It says that the attractive force, that's Fg, the attractive force between any two masses, that's m1 and m2 measured in kilograms, is equal to their product, that's m1 times 2, over r squared, where r is the distance between the two centers of mass, right? Now, what is this big G thing here? You know how little g, 9.8, is a constant? Well, big G is also a constant. This constant is called the universal gravitation constant. Now, notice how small this number is. Don't worry yourself on the units here. That's just to help everything come out in newtons at the end. This 6.67 times 10 to the negative 11th is a very small number. And in our universe, we believe that number to be true everywhere. In other universes, that number might be different. It might make gravity more significant in those universes. So let's talk about this. In our universe, gravity is the weakest of the four fundamental forces. In order, they would go strong nuclear force, electromagnetic force, weak nuclear force, and then gravity. It's weaker than the weak nuclear force. Gravity is the weakest of the four fundamental forces because in our universe, G is so small. In fact, in order to make the gravitational force apparent, I need at least one of the objects to be very big. So let's show you what this looks like. Let's say I take a 60-kilogram person attracted to a 1,000-kilogram car. The person and the car have a center of mass that's 1 meter apart. But see how small that 6.67 times 10 to the negative 11 is? That means in our universe, these two masses barely attract each other. That's not enough to overcome friction. If that's me and my car, a 60-kilogram me and a 1,000-kilogram car, I'm not going to go gravitationally attracted to it through the air. All the friction and air resistance would cancel that out, no problem. In order to make the gravitational force apparent, you need one of the objects to be very massive. One of the things I'm going to have you practice in the Google form today is going to be telling the difference of when you can use the local gravity equation versus the universal gravity equation. Let's start with local gravity. The local gravitation equation should be used whenever possible because it's easier to use. However, it's not always applicable. For astronauts on the space station, for planets orbiting each other, that equation doesn't work. This equation only works if you're talking about the force attracting an object, like a person or a car or a coffee cup, to a planet-sized object, something large enough to have its own meaningful gravitational field. Local gravity would be between a planet and object. And so in that case, you can kind of see this as narrower. The local gravity equation can only be used sometimes, even though it's easier to use. Whereas the universal gravitation equation can be used on the surface of a planet as well as in order to calculate the force between any two objects. You can think of the universal gravity equation as always true, whether you're near a surface of a planet, whether it's between two planets, whether it's between two objects. Universal gravity can work between any two objects at any distance away from each other. So, our law of universal gravity. Let's say we made this more apparent. We use the mass of the Earth and the radius of the Earth. Now, if I'm a 60-kilogram person sitting on the surface of the Earth, I would need to use the mass of the Earth, which can be found in the chart on the back page of your homework assignment 5.1. And I need to use the radius of the Earth. And why is that? Well, that's because I need to measure r, the distance between the center of mass of me and the center of mass of the planet. R can't be 1 because I physically cannot be within 1 meter of the center of mass of the Earth. I would be very unhappy with that scenario. If I'm a person 60 kilograms sitting on the surface of the Earth, I substitute in m, the mass of the Earth, r, the radius of the Earth, because that's how far apart our centers of masses are, and I see I get 588 newtons. And you might be thinking to yourself, wait a sec, 60 kilograms, 588 newtons. Couldn't I just have done 60 times 9.8? You are right, my friends. Yes, you could. So enjoy my stick figure drawing here. In this picture, my stick figure on the center of the Earth is in a uniform gravitational field. That uniform gravitational field is due to the mass of the Earth and the radius of the Earth. As long as I'm near the surface of the Earth, I could technically use either equation, but I would prefer to use the mass times 9.8 if I can get away with it. So, closing thought, let's think about gravitational field then. What exactly does it mean and where does it come from? Gravitational field, the way we're going to express it, comes from the fact that the local gravity equation and the universal gravity equation must be identical to each other for surfaces near the surface of a planet. If that's true, let's say my 60-kilogram person near the surface of the Earth, I should be able to calculate mg or the universal law of gravity. Just for your notation here, the big capital M in this equation, m1, that's going to be the mass of the Earth, whereas m is the mass of my person. Notice that the little m's cancel out, and that leaves this g, the gravitational field of an object. In this case, the gravitational field of the Earth, big M, depends on the mass of the Earth, big M, and the radius squared of the Earth, and a universal constant. Gravitational field is the distortion of space around any object due to its mass, but you and I are mostly going to calculate gravitational fields of planets because planets planets have meaningfully large gravitational fields. You need a lot of mass, m, to make this gravitational field big enough to measure or be meaningful. So, from your notes today, I want you to answer the few questions in the Google Forms. The Google Forms is going to get at comprehension of key concepts, whereas the Homework 5.1 is going to help you practice those calculations. Best of luck.